Good morning, dear students. Today we are going to start a new lesson from chemistry, acid, bases and salts. Acids are very important compounds which are used extensively in industries, in our daily life, and even the body of living organism contains acids in the form of fatty acid, amino acids, and hydrochloric acid, which is present in the gastric juice. The question arises, what are acids? Actually, there are different explanations, different definitions of acids. Definition by a Swedish chemist Svante Arrhenius. Then we have Bronsted and Lowry definition of acids, and Lewis acids and bases. But in this class, 10th class CBSE, we shall discuss only Arrhenius theory of acids and bases. Consider these examples. Hydrochloric acid, when dissolved in water, dissociates to produce hydrogen ion and chloride ions. Sulfuric acid in aqueous solution dissociates to produce hydrogen ions and sulfate ions. Ethanoic acid in aqueous solution partially dissociate to produce hydrogen ions and acetate ions. So what is common in all these reactions? That all these compounds are producing hydrogen ions when they are dissolved in water. This is the Arrhenius definition of acids. The acids are the compounds which, when dissolved in water, dissociate to produce hydrogen ion. Hydrochloric acid, sulfuric acid, nitric acid, carbonic acid, ethanoic acid, methanoic acid, they are all examples of acids. We shall discuss some common properties of acids. Action on indicators. So question arises, what are indicators? Indicator is a compound, is a substance which changes its color to tell whether the given solution is an acid or a base. What is an indicator? An indicator is a compound which tells us whether the given solution is an acid or a base by change in its color. Most common indicator that we use in our laboratories include litmus, methyl orange, and phenolphthalein solution. There are two types of the litmus: blue litmus and red litmus. As the name indicates, in neutral state, methyl orange is orange in color, and phenolphthalein solution is colorless. When a blue litmus paper or a drop of the litmus solution is added to an acid, blue litmus turns red. Similarly, when a strip of red litmus is dipped in a base or a few drops of red litmus are added to a base, they turn blue. When methyl orange is added, it is liquid. In an acid, it changes its color from orange to red, and in a base, it changes its color from orange to yellow. Phenolphthalein solution, which is colorless, has no effect in acid, but in a base, it changes its color to pink. So it is clear from these examples, the indicators are the compounds which tell us whether the given solution is an acid or a base by change its color. So, all acids turn blue litmus, red turn methyl orange, red and have no effect on phenolphthalein solution. So all acids turn blue litmus red, turn methyl orange, red, and have no effect on phenolphthalein solution. Reaction with metals. It is a generalized reaction. Acids react with metals to form corresponding salt and liberate hydrogen gas. For example, hydrochloric acid react with zinc to form zinc chloride and liberate hydrogen gas. Similarly, sulfuric acid reacts with zinc to form zinc sulfate and liberate hydrogen gas. Metals like potassium and sodium are highly reactive and they react vigorously with acids to form corresponding salt and liberate hydrogen gas. Here, one thing is to be noted that acids do not react with all metals to liberate hydrogen gas. Acids actually react with those metals which are above hydrogen in the reactivity series. So, the most common metals which are above hydrogen in the reactivity series include potassium, sodium, magnesium, calcium, aluminium, zinc, iron, lead, tin. These are most common metals and they are all above hydrogen in the reactivity series. So they will react with acids to form corresponding salt and liberate hydrogen gas. One more thing. Nitric acid is also a very important strong acid, but it does not liberate hydrogen gas with metal, even those metals which are above hydrogen in the reactivity series. Why? Nitric acid is a strong oxidizing agent, and its oxidizing property can be understood by this reaction. Nitric acid also reacts with metals. It also liberates hydrogen gas. But the hydrogen gas formed is oxidized to water. Therefore, nitric acid does not liberate hydrogen gas even with those metals which are above hydrogen in the reactivity series. Very dilute nitric acid, however, reacts with metal like manganese to liberate hydrogen gas. Reaction with metal carbonates and bicarbonates. All acids react with carbonates or bicarbonates to form corresponding salt, water, and liberate carbon dioxide gas. So you easily predict what would be the products when an acid reacts with a carbonate or a bicarbonate. For example, hydrochloric acid reacts with sodium carbonate to form salt, corresponding salt, sodium chloride, water, and liberate carbon dioxide gas. Similarly, sodium bicarbonate or sodium hydrogen carbonate reacts with hydrochloric acid to form salt, sodium chloride, water, and liberate carbon dioxide gas. Eggshell, which is actually calcium carbonate, react with hydrochloric acid to form calcium chloride, corresponding salt, water, and liberate carbon dioxide. Carbon dioxide is a colorless, odorless gas. It can be identified by passing through freshly prepared lime water. Lime water, which is colorless, turns milky when carbon dioxide gas is bubbled through it, when carbon dioxide gas is passed through it. So lime water is calcium hydroxide. When carbon dioxide gas is passed through lime water, it turns milky due to the formation of insoluble calcium carbonate. So you can detect that the gas which is given out, which is liberated or evolved when an acid reacts with a carbonate or bicarbonate by passing it through the freshly prepared lime water, which turns milky. However, this milkiness would disappear if carbon dioxide is passed in excess. What happens actually? When excess of carbon dioxide is passed through the product, that is insoluble calcium carbonate and water, and carbon dioxide in excess, soluble calcium bicarbonate is formed, and it is colorless. So the milkiness disappears when excess of carbon dioxide is passed through the lime water. So let us recall, carbonates and bicarbonate react with acids to liberate carbon dioxide gas. Carbon dioxide gas is a colorless and odorless gas. It can be detected by passing it through lime water, which turns milky. And what is this milkiness due to? This milkiness is due to the formation of insoluble calcium carbonate. However, this milkiness disappears when excess of carbon dioxide is passed through the solution. That's all today's.